Now, in this 7th lecture, we will see the another high frequency transmission structure, that is waveguide. As I already said, that waveguide is, it propagates non-TEM modes, that is both TE and TM modes propagate through through waveguides. Now, waveguides means it has its cross section is uniform. Now, that cross section, actually it is a cylindrical structure. The cross section may be rectangular, may be circular, may be elliptic. Depending on that, we say whether it is a rectangular waveguide, whether it is an elliptic waveguide, whether it is a circular waveguide, etc. So, it is a very popular one, rectangular waveguide, like a hollow rectangular pipe. So, that we will see support some interesting modes, and that is why it is popular, that its field structure etc. is very convenient to excite that type of mode in rectangular waveguide is very popular. So, almost in all the applications of microwave engineering in high frequency, particularly in the gigahertz range, rectangular waveguide is used, but we will see that sometimes we need a circular symmetry, that time circular waveguide is also used, that we will see in the next lecture. So, rectangular waveguide, it is a single conductor transmission line, as the waveguide says. So, you see this is a closed waveguide structure, closed metallic structure, conductor boundaries parallel to z axis. This is our custom, you can take it to any one, but generally we say that wave will propagate in the z axis direction. So, conductor boundaries, they are parallel to z axis. Now, arbitrary cross section, but generally we work with, it can be theoretically any arbitrary cross section, but generally we work with, as I said, rectangular structure or cross section or circular cross section, etc. The structures are uniform in z direction. In z direction, they do not have any variation. They are infinitely long in z direction. Infinitely long means that it is far away from the source, far away from the load, so that those discontinuities etc. are not there. So, a pure mode is propagating through these, and these metals are perfectly conducting, but you know that no real metal is perfectly conducting. That is why we will see that they will, any real metal, that since it is not an ideal metal, ideal conductor. So, there will be some losses in the conductor. Now, this is a generally this a standard waveguide, rectangular waveguide standard is called WR90. Actually, this WR, there are various things, 36, WR70, etc. Now, this WR90 is actually used in radar bands, X band. X band is one of the radar band, generally military radars operate there, and also in laboratories etc. we use this WR90, because this X band 8 to 12 gigahertz, these dimensions of the waveguide, they are depending on the frequency they are chosen, and this is quite convenient dimension. That is why WR90 is a standard, and WR90 waveguide means an X band waveguide. This is a picture, you see within this hollow metallic pipe is there. This is a larger one, actually the rectangle cross section is this is 0.9 inch, that is 2.286 centimeter in length, and 0.4 inch, that is 1.016 centimeter in width, but this is called flange, this is much larger than that, this is also rectangle. So, here two waveguides or two components, you can connect them together. So, there are holes here. So, by these 4 holes at the 4 corners, two structures get thing, so that this mouth of this waveguide and mouth of the waveguide which is connecting with it, they are flushed together, so that there is no discontinuity, no air gap there. Okay. So, this flange helps to make connections with two waveguides, so that there is no discontinuity created between the mouths of two waveguides. Now, for our analysis, this will be the structure. You see the generally the length of the rectangle, or that is called A. Now, we are taking one of the corners, the left hand corner as the origin. So, it is A. You see in some books or sometimes we take center as the origin, that time this side is A by 2, this side is minus A by 2. Similarly, plus B and plus B by 2 and minus B by 2, but we are taking this geometry, this convention that this is our 0. So, this is our B, that is the width of the rectangle or lower side of the rectangle, that is B, and higher side is A. So, we say that this wall is the broad wall, this wall is the narrow wall. So, broad wall is of length A and narrow wall is of length B. So, there are 4 walls. One is the top wall, this is metallic, the bottom wall is metallic, side wall is metallic, this side wall is metallic, inside there is hollow thing dielectric, it may be air or may be filled with any, completely filled with any dielectric. So, that is why we are saying that inside thing is a region through which the wave will go, that is a dielectric region. If it is not dielectric, it is free space. Sorry, another thing is that our propagation direction is Z. So, this broad wall that is in the x direction and the narrow wall that is in the y direction directed. Now, so we have already seen when we have seen TEM mode that if you have a hollow pipe is a single conductor, waveguide is a single conductor. In a single conductor you cannot have TEM wave because you do not have any voltage between the two wave, because all are same structure. So, their potential difference is 0, that is why you cannot have any transverse electric and transverse magnetic field, that we have already seen. But both TE and TM possible, whatever I said. Now, let us start that for TE modes, transverse electric, we know that the longitudinal component of the electric field will be 0. So, if we do that, then that means we will have to express all the 4 transverse fields if they are present in terms of the longitudinal magnetic field, because Ez is not 0. So, sorry, in TE modes obviously Hz will be present. So, the transverse component of Hz, that is small hz x y. So, we will write the Helmholtz equation in terms of that, and then we will apply separation of variables, this we have already seen. So, you know all this mathematics. So, again you are getting 2 constants, this side also this is a function of f, this is a function of g, but it is said that these 2 functions they are equal to, their sum is equal to a constant, because my kc square is a constant. So, that is possible only if separately they are equal to 2 constants. So, that is this. Now, its solution, you know all these 2 solutions, again you can see that this d2f dx2, that means double differential of the function f with respect to x, that will be, if you take this side here. So, that will be constant into the function, that means again some cos sine type of thing. So, this is in x. So, that is why cosine of x and sine of x. Similarly, for g you have y. So, cosine in y variable, sine in y variable. So, this is a general form that you know. Now, you find out the transverse components once you know. So, you see this is the transverse component, longitudinal magnetic field component Hz we have solved in this. A, B, C, D are 4 constants yet to be determined. So, now we have already developed, I remember equation 15, where we have expressed all the transverse field in terms of longitudinal fields. So, in terms of Hz, because Ez is 0 in this case. So, in terms of Hz we can write what is the Ex, it will be also involving this A, B, C, D and some form of cos and sine, because that depends on this differentiation, etc. Similarly, we can write uy in terms of this a b c d and this cos and sin functions, etc. Now, we can also do it for other two thing. Now, let us put the boundary condition. What is the boundary condition? That you see the in the top wall and bottom wall, it is a conductor. So, in the conductor there are, that means this plane is which plane? It is yz plane. So, tangential electric field on this bottom wall and top wall should go to 0. Now, tangential electric field means on the top wall, let us say tangential field means either it will be an Ex field or a Ez field, but in a TE mode Ez field is not there. So, boundary condition is Ex at this one is 0 for y is equal to 0, that is the top wall, sorry, y is equal to 0 is the bottom wall and y is equal to b is the top wall. Similarly, we can say that what will happen to the side walls, left side and right side, they are also metallic conductors. So, they are also tangential thing will be 0. What is tangential there? Obviously, one z component, but we do not have any z component. What is the other component? Y component. So, Ey should go to 0 there, where at left side wall and right side wall. So, put this boundary condition, if we now put into those solutions that we got, that means Ex, Ey, Hx, Hy, whatever we got. So, in that for Ex, Ey, if we put this, then we have put this and force that to that 0. So, Ex x 0 is equal to 0, that implies that this is this one, it total thing is 0, means that you cannot have any other thing except saying that d is equal to 0. So, by that you can find out what is Ex, and also for b you can put that it will take this value ky. So, similarly, if we put the other boundary condition, that gives you b is equal to 0 and kx takes some discrete values, those are given by this like ky, and so we can write the here all the 5 fields. Generally, we have 6 fields, 2 transverse for electric field, 2 transverse magnetic fields, 1 longitudinal electric field, 1 longitudinal magnetic field. But in case of T field, 1 longitudinal E field, that is Ez is 0. So, we are writing Hz, Ex, Ey, Hx, Hy. So, all this constitutes the solution of the field. So, that is field analysis, that you have now come out from that basic wave equation, you can find out this. So, that is why we have developed those modes and T modes characterization, because now you see it becomes very easy to find out the fields. Now, also that time we have developed what is beta, beta is this. Now, we have seen that this Kc, sorry, this Kc is here, that ky square plus kx square is Kc, ky square is by boundary condition they have been fixed to some discrete value, kx also to discrete value, that is why beta will be this discrete value, that beta will be k square minus this. So, these are the numbers m and n, they are the mode numbers. So, T E M N mode. So, now you see that we want that if wave to propagate, then beta should be a real quantity, as I was saying, that otherwise it will become an evanescent mode. We want a propagating mode. So, beta should be real. Now, beta should be real means this under square root thing should be positive, that means k should be greater than 0 kc, or k should be greater than this value. So, we know the value of k, that is a wave number, that was a constant, that was, if you remember that time we have put k is equal to omega root over mu epsilon. So, that should be greater than this. Now, this On the other hand, if k is less than kc, you see propagating when k is greater than kc. Now, k less than kc, that time the condition is this. Now, omega is nothing but angular frequency. So, we can find the corresponding frequency. So, you see that below, if f is below this value is given by the mn's number, then the wave cannot propagate. Wave won't be able to pass through the waveguide. So, this is a stark contrast to the TEM line, as we have seen that any frequency can pass through a TEM line, but in a waveguide both for TE and TM mode we see there is a cutoff. So, and that frequency we have calculated that f is less than equal to this. So, if we take that equal to value, so that means frequency, all the frequencies below this cutoff, they will be wave won't be able to propagate. So, you need to have a frequency above this, then only the wave will propagate. So, that is why these waveguides are called a high pass filter. So, low frequencies are not passed, but all the high frequencies after this cutoff is passed, and this is given by this. So, all the signals with frequencies below this cutoff cannot propagate through a waveguide. All the signals with frequencies higher than cutoff frequency can propagate in a waveguide. Now, so there are many modes depending on the value of m and n. You see that when we say this, so various values of m and n can be any number, any integer. M and n both are starting from 0, any integer. So, there can be various modes, T modes, but out of that the one with lowest cutoff frequency is called dominant mode. So, let us say that lowest one will be m and n both are 0, but if m and n are 0, if we go back to the field equations, here if we put m and n 0, you see by putting n is equal to 0, Ex is 0, by putting m is equal to 0, Ui is 0, by putting m is equal to 0, by putting m is equal to 0. So, if m and n both are 0, here also you see that if n is equal to 0, so sin 0, so this is also 0. So, all the fields Ex, Ey, Hx, Ay all are 0. So, that is not a physical solution. So, we say that this is not acceptable. So, m is equal to n, that means T00 mode, TEMN, you see the first subscript is m, the second subscript is n. So, TE00 not possible in a waveguide. Now, since A is greater than B, that is our convention. So, lowest cutoff frequency occur for m is equal to 1, n is equal to 0, because m is related to A. If you look at that m pi by A, so that will give you the frequency, and that frequency is nothing but 1 by 2A mu epsilon. Mu epsilon are the parameters of the thing. If it is a air waveguide, these are the mu and epsilon are the free space values, and A is the broad dimension of the waveguide. Now, this dominant mode is called TE10 mode. It is a very interesting mode, and if you have a waveguide where more than one mode is propagating, we call it waveguide is over moded. So, in over moded thing, power is transported by all the modes which are propagating. So, you need to separately excite the modes. Similarly, if the modes are taking power, you need to extract the modes separately. So, that creates an engineering problem. Also, when you have one type of mode extraction, the other power that are carried by other modes, that gets wasted. So, generally we try to make a waveguide non-over moded. Now, the wave impedance, remember it is, we cannot have characteristic impedance here, because we cannot define V and I. Characteristic impedance is a low frequency concept, but this wave impedance, that is always there, as we have already discussed earlier, that wave impedance is a fundamental property of the wave. So, that will be k eta by beta. Various modes will have various betas. So, actually we should have written beta mn, similarly here j t mn. So, that various t modes, t mn modes, they will have different wave impedance. Now, wave impedance z t is real when beta is real, because k is a number, it is a real number for simple material. Eta is real number, intrinsic impedance of free space equal to 120 pi or 377 ohm. So, if beta is real, z t is real. Now, beta real means we have seen that when the wave is propagating or we have a propagating mode. So, by looking at wave impedance, you can see that whether you have a propagating mode, if you have a beta imaginary, then z t will be imaginary, and you can say that okay, I have an evanescent mode. So, I cannot transfer power through that evanescent mode. Evanescent modes will die down after some time, because its beta will actually, instead of wave propagation e to the power minus j beta z, it will be e to the power minus j again j beta z. So, that will be a loss, e to the power, it will be contributing to the attenuation of the wave. So, that is why after some time it will be propagating. Now, this is a picture of wave impedance. So, you see x axis is f by f c. If we are above f c, then the both T and T m modes, their impedance, wave impedance is real, that is why it is shown as R naught, but when they are less, then the impedance is reactive, and for T mode this is the variation. Up to here you see that just before the cutoff it is shooting up to a very high reactance. Similarly, just after cutoff it is gradually decreasing and coming to this value, intrinsic impedance value, this is eta. So, intrinsic impedance value. So, when you are further away from cutoff, that means quite high from the cutoff frequency, you approach the impedance of eta. Guided, you see this is from a book, I do not remember the book, it is characteristic impedance of waveguide modes. Now, this is wrongly written, this is not a characteristic impedance, this is talking of wave impedance, that is why I have given this heading as wave impedance. It is from some good book, but they are writing characteristic impedance. This is basically the electric field to magnetic field ratio, this should be called wave impedance, not characteristic impedance. This is a loose talk, but you should know that it is a wave impedance concept. Now, similarly, guided wavelength and phase velocity can be easily calculated, we have already seen. So, since beta is greater than k, so wavelength inside guide is larger than free space wavelength. So, if you have a 10 gigahertz signal, that wavelength is 3 centimeter, but when it passes through any waveguide in the T mode, then its wavelength is more, maybe 3.5 centimeter or something. Also, the phase velocity, you see we are showing here that why it is so, because these values you see k, actually for TEM mode beta is equal to k, that we have already seen, and since this beta is less than k, that means that in T mode the phase constant beta is less than this wave number k, we get that lambda g, the guided wavelength, is greater than free space wavelength. Similarly, for phase velocity, for the same reason phase velocity is larger than this. Now, what is this velocity? This is, if it is in free space, 1 by this, actually if you put this value, because these are constant, this will come to be 3 into 10 to the power 8, that is the speed of light. So, inside an waveguide, the T mode phase velocity is larger than the velocity of light. So, you can have a fast wave, we call it any wave which is faster than the velocity of light, that is fast wave. So, inside waveguide you have fast wave, that is why waveguides are called first wave structure. Now, dominant mode, if we T10 mode, it's if we know it Ex is 0 everywhere, that means it does not have an x component, you see it only have an y component, and that y component is, oh there is a mistake, it will be sin n pi x by a, Ey is equal to Ez is equal to 0, Hx, this also should be n pi x by a, and it does not have any longitudinal component. Similarly, H does not have any y component, but H has a Hz component. So, let us see the structure. If we see the structure looks like this is a 3D structure. These red things are, you see, if I take this cross section, this is the cross section, there you see electric field at the center, it is very high, its electric field is vertical, or from top wall to bottom wall it is coming electric field, and you know field lines when they are dense means its value is very high. So, at the center its value is very high, at the sides its value is very less. Whereas, magnetic field, you see this is on the top wall, the magnetic field is like this, you see, and in the central portion there is no magnetic field. Also in the side wall, you see at the center there is a very dense or very high value of magnetic field, gradually at the sides it is there. This whole structure repeats after every lambda g by 2, okay? And currents also we have seen. Let us see some better structure for better understanding. So, you see electric fields, they are from top wall to bottom wall, they are flowing, whatever I said. The green ones are magnetic fields. So, magnetic field is like this, and you see that the whole thing is getting repeated, magnetic field in the along the longitudinal direction after every lambda g by 2. And current distribution, if you see that this is the current distribution, but this one is a bit wrong actually. Central portion there is no current, because you see that in the central the magnetic field is like this. So, central portion there are no currents, longitudinal current is not there at the center, other places there are longitudinal currents. That is why what happens, you see, since the magnetic field is not there, we can cut a slot there. So, if we cut a slot, a very small thing, we can probe inside the waveguide. Actually, that is the way by which the field inside waveguides etc. are measured. We have already discussed in an earlier NPTEL lecture that how to measure impedance, how to find fields etc., and you can see that lecture. So, there we all use a, in the waveguide, in a slotted waveguide we have a slot cut at the middle, that we can do because of this dominant mode, it does not have any current here. So, we do not disturb anything, the magnetic field is here. Here you can see in a better way, you see the magnetic field, if I go by the central one, if I go along the center, there are no magnetic field. So, if I cut a slot, I am not disturbing any magnetic field, because otherwise you see that if I cut a slot and disturb the field, basically I am disturbing the whole structure. So, what I am measuring is not the proper, but due to this fine variation that at the central portion there is no magnetic field, and also you see that the at these portions there are currents are minimal. So, I can easily cut a slot and I can probe what is happening. Another beautiful thing is, if I do it at the center, we have already seen that in this cross section the electric field is maximum. So, when I am cutting the slot, I am not disturbing the magnetic field here, obviously electric field cannot be here because this is a TE mode. So, no longitudinal electric field, but here at the center the electric field is maximum. So, in all the cross section the central field is maximum electric field. So, the beauty is when I am sensing, I am sensing the maximum, with maximum sensitivity I can sense, because electric field is maximum there. That is why the slot is cut at the middle in a rectangular waveguide, which is working with T10 mode. So, electric field is vertical, maximum at center, 0 at side walls and varying cosinusoidally along a direction. Displacement here H field has both Hx and Hz component that we have already seen. Hx is maximum at center, 0 at side walls, etc. So, the longitudinal slot at center won't disturb magnetic field. E field is best for sensing a sensor because it is highest. So, these are other mode structures and there you see that there are the magnetic field is there are you see if I put the cut a slot here, there will be magnetic field gets disturbed because this magnetic field is there. Suppose I cut it here, there is a magnetic field here, I cut it here, there is a magnetic field here. So, only for T10 mode we can cut a slot there. That is why for all experimental purposes or for any sensing T10 mode is preferred. Now, these are some other field structures. Also you see that there are some field structures which are not uniform, but this is an uniform. Our dominant mode T10 field electric field that is uniform. So, we require uniform fields, then we can have various other things. And wave impedance. So, cutoff wave number is this, phase constant is this, wave impedance you see it is less is this. So, if you do lambda by 2a, now wave impedance, this is intrinsic impedance, this is 377 ohm, but this T10 mode its impedance wave impedance is much larger than this intrinsic impedance. So, for a WR90 waveguide at 10 gigahertz if you do, because I know what is the value of A, 10 gigahertz means 3 centimeter. So, this wave impedance is 505 ohm at 10 gigahertz. Power flow, we have done these calculations, and for propagating modes P10 is non-zero real power. So, also dielectric loss we have already found the expression. So, this conductor loss if you do actually all these mathematics how to arrive at this expression that will be given in your notes which will be uploaded, you can see from there, but basic things we have already in the first 5 lectures we have given you the how to calculate that, these are all applications of that. So, if you see that attenuation of the dominant mode, you see this is the dominant mode. So, initially just though the mode starts after this roughly near about 5-6 gigahertz, but attenuation is changing very fast, but after some time the attenuation stabilizes and it is quite small. That is why people use it from 8 to 10 gigahertz, though the cutoff starts at 6 gigahertz, but near that the attenuation is varying, but after some time attenuation stabilizes. So, it can use, but you cannot use it greater than 12 gigahertz, because after 12 gigahertz we will see that the next higher order mode, that is T01 mode, not T10 mode. T01 mode also have a, this is T01 mode, this is the next mode that comes, then one TM mode comes. Okay. So, this is the thing that first T10 cutoff takes place, as I said roughly 6 gigahertz, then TE01, these are the thing. This is other modes will start coming, and then T20 cutoff that comes, but TM11 cutoff that comes around 12 gigahertz. That is why after 12 gigahertz people do not use it. So, this is for this is a structure that you can have this diagram to find out what is the attenuation as well as what is the cutoff. Now, similarly hurriedly we will see TM mode, here Hz is equal to 0. So, here the Helmholtz equation will be in terms of the longitudinal E field Ez, again with the separation of variable, again the boundary condition is the in the side wall what is the electric field tangential component, that will be in the side wall, it will be E z, and in the top and bottom wall it is E z. So, you force that, by that you get those values, and again those k x and k y are some discrete values. So, transverse components you can write once you determine E z, you can write E x, E y, H x, H y, phase constant, same expression. So, cutoff frequency lambda g V p or now field expression suggests that if here it suggests that if either m, here you see that this is a bit different from the transverse magnetic field, and if either m or n is 0, all the transverse components are 0. So, T m 0 0, T m 0 n and T m m 0 modes cannot exist, because all the fields go to 0. So, only thing is dominant mode, that means the first one that can start is that it should be both 1. So, dominant modal wave impedance is given by this, cutoff frequency this. Now, if we compare with T mode, because this is dominant T m mode, T m 11, and this you compare that T m 11 is this, obviously it has an extra baggage of this, that is why the cutoff frequency for T 10 mode is less than cutoff frequency of T m 10 mode. So, among all the combined T and T m mode, the T 10 is the dominant mode. Now, you can see that T 10 mode starts at that, what I was saying, that T 10 mode for WR 90, that means this as I said 0.9 inch and 0.4 inch or these centimeter values. T 10 mode starts at 6.56 gigahertz, T 20 mode starts at 13 gigahertz, T 01 mode starts at 14 gigahertz. That is why before the onset of T 20 mode, you should not go beyond that. That means, that is why we generally WR 90 is operated up to 12 gigahertz. It is operated up to 12 gigahertz, so that T 20 mode does not come there. Now, you see that 3 T modes come, then the next one, that T 11 and T m 11, they come together, then T m modes start propagating. And these are again the, if you change the dimension, you see A by B we call rectangular waveguide, but what happens if we make A by B 1, that is a square waveguide. Now, in case of square waveguide, you will see that it is a overmoded waveguide. The when T 10 is propagating, that time also T 01 propagates through it. So, that is why there are problems, because these two waves have different orientation of electric field. So, but if you want that, in some applications you want that electric field should be in the both the direction, there square waveguides also is used. Now, these are the methods of excitation of various modes. So, as various modes are different field structures, so you need to excite the field structures differently. Like TE 10 mode, generally what we do at the central position, we put that coax, its central conductor we connect to the waveguides wall where the electric field is dominant, and then it starts electric field from there. Whereas, in case of T m 11, we from the side wall we try to excite, like that. There are, if you look at the electric field and magnetic field structure, you get the clue that how to excite the field. These are just you to know that okay, this type of thing you see that at the central portion you put a coaxial cable and connect the central conductor to the waveguide bottom layer, you get a you make that perturbation and you get the excitation of modes. So, I think that is all about waveguides. In the next rectangular waveguides, in the next lecture we will see the circular waveguide geometry.